Good day. Welcome to Discrete Mathematics. Today we will be discussing about switching network. So what's a switching network? Now, switching network is just like a connection of different switches. No, just imagine your just imagine your switches in your homes, in your houses. So the purpose of switches is to turn on or off something. Okay, for example, for a light bulb, so you can switch on the light bulb or switch it off, turn it off. Now, this is just a short discussion. Now, I'll just present to you representing expressions, okay, logic expressions into a switching network. Okay, now in a switching network or in a switching circuit, we have a collection of switches and wires. Okay, when we say uh, of course, we cannot create a network or a connection, or a circuit if we don't have or if we don't use wires. Then we have two types of circuits or switches rather. We have the open and the closed switch. When we say open, so that prevents the current from flowing. So if we will compare it to a light, no, a light bulb. So open, we can say that the switch is or circuit or the network is open if the light bulb is not emitting light. Okay, it's closed when the light bulb is on. So when it's closed, it means that we allow the current to flow, okay, uh, through the switch. Okay, again, open is say off, closed is on. Okay, open is we don't allow the current to flow, closed is we allow the current to flow in the switch. Okay, so these are the definitions. Now, aside from these three basic terms or fundamental parts of or components of a switching network, singles, wire, open switch, and closed switch, we also have types of switches. We have series or parallel switches. Later on, I will be showing to you what's the difference between these two. Okay, here are some examples or now truth tables of a network switching in series and parallel circuit. So let's try to check how can we relate a series and parallel circuit, or how can we differentiate the two to our previous discussions. Now here is a truth table for using logic, the logic symbols or the connectives. We have the use of conjunction and the use of disjunction. So instead of using true or false, we will use close or open. Now when we say close, so that means we allow the current to flow, so that's equivalent to true. Open, we do not allow the current to flow, so we compare it to false. Okay, now for a we can compare a series circuit to a conjunction, because in a series circuit, when one switch is open, therefore the flow of the current will be hindered or stopped. No, the circuit to will not allow the current to flow. In parallel is that when one or more switches is closed, then we can allow the current to flow. So that is why we have these values. Okay, it's just like this one. Now if you compare the series to a conjunction, you have true, or when the switches are closed, then the series circuit is closed. Okay, however, when on one or more switches or points or say nodes are open, then the series circuit is open. Okay, here is a diagram for parallel and series circuits. As you can see, okay, I'll just change this. The for a series switch, okay, again it's equivalent to a conjunction. For a series switch, when one switch is open, then it will not allow the current to flow. For example, if we close the symbol for a closed circuit switch is this one. No, for a closed switch, say this is switch 1. Okay, when switch 1 is closed, no, if this is the flow of the current, we'll just say this is the flow. But ideally, it's in the negative, the flow. But we'll just use this one. Now, in switch 1, the current will flow. However, when it comes to switch 2, so since this is open, so the circuit will, or it will not able to light the bulb. Okay, this is an example of use a series switch. However, in a parallel switch, when only one, say this is closed, though, which means the current can flow. Okay, the current can flow to this switch or to switch 1, and it will make the bulb light. Okay, if both are closed, then same, no, it will light the bulb. However, if switch 1 is open, switch 2 is closed, of course the light will also, or the bulb will also be lit up, diba? So this is the flow. Okay, if this is closed, no, so this is the behavior of parallel and series switches. Again, for a series switches, we can compare it to conjunction, wherein for us to be able to light this bulb, both switches should be closed, no, or true. Okay, both switches should be closed or true. However, in a parallel switches, it only takes one switch to be closed so that it can turn on this light bulb. Okay, so that's the difference of series and parallel switches. Now let's proceed to the next one. Okay, for a while. Okay, proceed to the next slide. Now when we say complementary switches, so these are just switches wherein when one is closed, the other one is open. I don't know if you have experienced this one or you have complementary switches in your houses, but again, this enables two switches, no, to perform oppositely. So when the other is closed, the other one will be switched on, switched off. When the other one is switched on, the other one will be switched off, and vice versa. However, we also have equivalent switches wherein they have the same electrical properties concerning the flow and non-flow of current, meaning uh, whatever the connection, now if we compare it in logic, that's logical equivalence. Okay, that's, we call them equivalent switches. Now you have here a sample problem. Okay, but we will be only answering number one. Now I'll be just showing you the how the switches works. Okay, because the next topic that will be the operations will be in detail. We will be dealing with Boolean algebra. Switches, I present switches as an introduction to Boolean algebra. Okay, going back, we will answer number one by finding the laws of equivalence. We will that this means that we will have to simplify this compound statement, and then we will create a switching network. Now I will be showing you two different solutions or two different approach when solving the this item. Now, if you'll recall your logical equivalence topic, I know you will be able to simplify this one. Now, let's check first solution number one. Now, in solution number one, we will focus on those inside the grouping symbols. So, this part here, if you recall distributive property, we can simplify this part to this one. Okay, please check your laws, no, your table regarding the laws of equivalence. Then the result should be this. Then after, since we cannot simplify this anymore, so what will we do? We can distribute Q here and here. Okay, and the result will be this one. And after, as you can observe, we have now the same operators or logical connectives. So we can use commutative or no, associative law so that we can regroup it. So the result would be this one. Then we also have a law, no, a, a statement disjuncted with its negation or its inverse is just equal to true. And when true is disjuncted to any statement, the result would always be true. And when true is conjuncted to a statement, the result would be equal to that statement. So therefore, we can simplify this compound statement. Okay, this compound statement can be simplified to this one. Let's check the other solution. Now, in the other solution, we will be checking or using first associative law. Now, as you recall, if you recall, since we have operators, same operators, therefore we can use associative and or commutative law. But for this case, we will use associative law. So we'll be grouping these two. If you observe, we have variables here, same variables q. However, the other one is negated. Then we will have an idea what will happen when uh, when we negate it. Okay, so then using associative, then we can group, and after we can distribute no, this one, not q. So we'll have these and these. Okay, distribute q. Of course, we will have to include the connective. So we'll have this one and this one. Then after getting the disjunction, so q or not q is just equal to true, and true conjuncted with statement will be equal to that statement. Then after, so notice that we now have the same operations and we have here the same variable, so therefore we can group these, okay, using associative law. And recall the laws. Okay, this would be just equal to r. So therefore, if this is just equal to r, the final answer will be r or not q, and we got the same answer. Please review your laws of equivalence, the different laws of equivalence. Okay, so you just practice and practice, no, until you can uh, until you'll be able to answer problems. Now, how do we create a logical or a switching network for this one? Now, the simplified statement. So we have R or not Q. Now, we don't have symbol yet as of now. We will not get the symbol for not. So which means since this is conjunction, therefore it's a parallel circuit. Now we have two parallel switches. Now, and we know this is connected to your source, and this is connected to your bulb. Sorry. Okay, and you have R, and we'll just use not Q for this case. Okay, we will just put here the circle so that it's an indication that these two are connected to this wire. So this is our switching network or circuit for the simplified expression. That will be all for this topic, and thank you for listening.